Well, thanks a lot. Can you hear me well? Also at the back? Right. So it's really a pleasure to be here, of course. So I also want to thank the organizing committee, in particular the scientific committee, for having given me this opportunity to speak to SISBayes. Now, when I was invited to give this talk and I saw the word foundational lecture, foundational sounds a bit intimidating. So I said, well, you have to say something that is really giving some future perspective on it. But then I saw the good news. I said, well, I don't have to speak only about my own work. I can speak about something that is really a topic in which I believe there is a future direction also for statisticians, in particular for statisticians. Then I thought about it, and eventually I landed on this title, From Statistical to Causal Models, but it's rather the model is more about causal inference and causal reasoning, perhaps, since I will just touch upon models only briefly. And let me tell you how I got to this topic. It was a sort of slow evolution because I started several years ago working on graphical models. And graphical models, as most of you know, I think, are very powerful to describe multivariate distributions, to encapsulate dependencies across variables. But then, over the years, I realized that there was also another side of graphical models that was very useful, namely causality. And so I started working on causality, or rather, I should say, studying about causality. I'm still studying a lot because the topic is so huge, and I am relatively new to the causal side of graphical models. I'm more involved with the graphical models per se. And this interest in causality actually was accelerated when the machine learning community, the artificial intelligence community got interested in this. So that was a strong acceleration that gave me also the feeling that there was something that we should investigate more thoroughly. And that's the reason why I chose this topic. I wanted to present it to you. If you never heard about causality, don't worry. This will be a broad lecture, covering, the basic aspects of it. I will be extremely simple, but, some of the concepts are profound. So I think they are worth thinking carefully about it. Now, one other aspect I wanted to touch upon is that I will be looking at causality from a particular perspective, namely the perspective of graphical modeling. And I must give immediately a disclaimer, that's not the only way to look at causality. In fact, there is at least another view of causality, which is, of course, linked, but has a different flavor, which is the one based on potential outcomes and is connected to the names of people like Don Rubin and Guido, for instance. So I will not discuss that, not because I believe that it's not worth it. In fact, I think it's extremely worth it. But given the time constraint, I think just focusing on one aspect, the one it's closer to my interest, but above all, it's the approach which I believe is closest to the machine learning and artificial intelligence community. So I believe that statistics must more and more, it's already taking place, but must more and more interconnect with this world, the machine learning world and the artificial intelligence world. It's not just a bridge, I think. It's more than a bridge. It's really a synergy between the two worlds, the statistics world and the artificial intelligence world. And that should create cross-pollination between these two worlds. It's already doing, we should be doing. And if somebody among you decide to embrace this topic of causality, I think this would be a great investment. All right, so let me start by giving you a brief outline. And first of all, how important is causality right now in the scientific arena? Well, it has already received quite a lot of awards. In particular, in 2011, Judy Appel, who basically invented this approach to causality from the graphical model perspective, at least in the modern interpretation, was given this award, and you can see there the motivation for fundamental contributions to artificial intelligence through the developments of a calculus for probabilistic and causal learning. And in 2021, the Nobel Prize for Economics, I mean, the actual word is a bit more complicated, but that's basically the way we call it, was given to an economist, David Card, but also to two further economists, Joshua Angrist and Guido Imbens, for their methodological contributions to the analysis of causal relationships. Actually interesting, David Card got half of the prize, and the other two got the remaining half. So I don't know how they decided about this, but one got $500,000, the other one got just $250,000, but still, it's a great recognition. Now, in 2022, another prize, the Rousseau Prize for Statistics, which was recently introduced actually by Professor Rousseau, a statistician who made also money. So with statistics, you can make money, right? It's not true for everybody, I'm afraid, but for some people it was true. So this guy made a lot of money, and so he decided to create a fund. It's a serious thing. It's actually recognized by the Belgian government. The Belgian king is actually the patron, and they give, I think, every 2 years a prize with some strict regulations. So they look at geography, they look at topics, of course, and they try to make a balance. And in 2022, it was given to 5 statisticians working on causality, and James Robbins is the major one. Again, he got half the price, and the remaining 3 got, the remaining half. So not much actually in terms of money, but in terms of recognition, it's quite a bit. And this guy here, this is Professor Rousseau, actually, is the founder of the prize. Right. This is just to say that causality is also recognized as an important element. Now, I spoke about already artificial intelligence and machine learning, and here I wrote a quote, I put a quote by Julia Pearl that I would like to read to you. The kind of causal inference seen in natural human thought can be algorithmized to help produce human-level machine intelligence. So according to Pearl, what's missing nowadays in artificial intelligence is causality. Once that's reached, if we reach that level, then probably we can start thinking about a truly human level machine intelligence or artificial intelligence. And another quote, this is by another major scientist in the field, Bernard Shirkoff. Some of the hard problems of machine learning and artificial intelligence are intrinsically related and by advances in our understanding of how to model and infer causality from data. This is a beautiful talk that was delivered by him in 2020 National Congress of Mathematicians. So a very large audience of people, mathematicians, comprising lots of scientists, also statisticians, but showing that causality is a major ingredient of advances in future machine learning and artificial intelligence. And now here, since we are now talking about causal artificial intelligence, here I just cited a few papers that I found, starting even from the title, where you can see that causality. This paper is about interpretable machine learning models and feasible counterfactuals. I will describe to you what we mean by counterfactuals. This is another paper, Causal Reasoning and Large Language Models. It's trying to study large language models from the behavioral perspective and to see how they are capable of generating causal arguments. I don't know whether you ever asked ChatGPT to provide something causal. I did try a bit, with mixed results, of course, but it's already there. Something is already there. And then in the medical field, of course, there is an explosion of papers about causal AI. And I liked the last part of this part of the abstract, where they say that a doctor aims to explain a patient's symptoms by determining the disease causing them, while existing diagnostic algorithms are purely associative. And that's actually the contrast I like to make. We as statisticians are used a lot to talk about association. correlation. That's great. I mean, we have done fantastic things, and machine learning has done lots of things just looking at the associative perspective. But the causal perspective is, of course, really what we are looking for. And we all know that quite a large number of statisticians deal with causality. So it's something not new to us. And that's why statisticians can give a strong contribution also to machine learners, because we have already quite a lot of the techniques. And we have to create this synergy so that this technique can really become much stronger. And another more theoretical paper that basically says that an agent, artificial intelligence agent that should satisfy some bounded loss function, so to speak, for a large set of distributional shifts must have learned an approximate causal model. So if you want to have an artificial intelligence agent that is acting, not just thinking, but also taking actions, and these actions should be taken in environments that change, if this has to be done in such a way that the loss function is controlled, then there must be some causal model behind the agent. Otherwise, that wouldn't work. This is a theoretical result. This is a theorem. And then finally, this paper, Causal Approaches to Post-hoc Explainability for Black Box Prediction Models. That's one of the big issues, explainability of artificial intelligence methods. And then causality can help in that direction. All right. So let me start with a very simple example. You probably all know this. Correlation is not possible. Sorry about this. Okay, I'll keep it here. That's why we tell our students that they should not confuse the two aspects. And this is the correlation between the rate of consumption of chocolate and the rate of Nobel Prize winners. Well, to understand causation, you have to think about manipulability and intervention. That's the crucial thing. And as statisticians, we are not quite familiar with these terms. Philosophers are, so there is this book by Woodward in 21, Causation and Manipulability. So from the very title, you see that manipulability is strictly connected to causality. And of course, the book by Julia Pearl, Causality Models, Reasoning and Inference. But causality has been around for several years in fields like epidemiology, agriculture, and of course, econometrics. Now, let me tell you the definition of a causal effect. A random variable has a causal effect on a random variable y if by changing the value of x, then the distribution of y after setting x to x prime changes, right? So here is an example. Suppose you have this association between a phenotype expression and a gene expression. They're clearly correlated, positively correlated, but what happens if I intervene on gene A? In some cases, this is possible. For example, if you do agricultural genetics, and in particular, if you knock out the gene. So knocking out means completely silencing the gene, say value 0. Well, you see the vertical red bar, there is a strong drop in the phenotype expression. So if you knock out the gene, the phenotype dramatically changes in its expression. That suggests that gene A has a causal effect, because by intervening exogenously on it, you change the range of values for the phenotype. On the other hand, take a look at this second panel. You have a new gene, gene B, and the association between gene B and the phenotype is very similar, actually, to the one we have above. So from the associative point of view, you don't see much difference. But if you intervene on the gene B in this case, at the red vertical bar, again, you knock it out, you see that the range of the phenotype expression is basically unchanged relative to the range it had in the association data. That suggests that gene B is not really causing the phenotype, but there is a confounder that that influence both gene B and the phenotype. And that's basically the idea. So you can formalize this in a principle saying that if two random variables are statistically dependent, then there exists a random variable z which causally influences both of them and which explains all of their dependence. That is, conditioning on z, you have independence, X independent of Y given Z. As a special case, Z may coincide with X or Y. So here you have the three situations, X is causing Y is causing X, and there is a confounder situation. Now, of course, in the chocolate case, we all know what's going on. Neither A nor B are true. But because we have background knowledge, the problem is so simple, we understand it. So what must be true in this case, explain the association between chocolate consumption and Nobel Prize winners, is the fact that there is a confounder that affects both, and this confounder can be something like education, investment in education. So it could be like a generic economic factor that is driving both aspects. This is easy because we understand it. The problem is getting to better understand the causal mechanism without having such strong and easy background knowledge. Is correlation useless? Not at all. So there is still a lot of things you can do by looking just at the association level, at the correlation level, and you don't have to use causality all the time. It's still great to know that both gene A and GB are associated with the phenotype expression, but this is okay if you look at the data from an observational point of view. You just see what nature produces. But if you want to actually intervene, if you want to answer questions following an intervention, then things change. Then you need a causal model. And I gave you two examples there, the gene expression, the knockout case, but also in economics, if you want to understand the effect of a policy enforcing a job training program. So you don't let people choose whether to follow the job training program, you actually force them in a hypothetical experiment to attend the joint program. All right, causal modeling. I want to start by giving you the definition of a causal graphical model. So a causal graphical model is a graph, in fact, is a directed acyclic graph, one with directed edges, where the edge between xj and xi means that there is a direct causal effect of xj on xi. And then a joint distribution, which describes how the random variables behave from a probabilistic perspective, and that's probably what most of you already know, is the product of the conditionals of each variable given the parents. PAI means the parents is the set of variables that have a direct effect on xi. Okay, so this decomposition of the joint distribution into causal conditionals is actually crucial. And I'll get back to this, hopefully, towards the end of the lecture, because it is one of the interesting things that is coming out in the machine learning community, how to actually organize the joint distribution into these causal conditionals. Here is the four-variable example. It's very trivial, of course. You see that the joint distribution factorizes in this way. Now, when you have a causal graphical model, you have the joint distribution, right? Now, an interesting thing that we all know, we've been dealing with that for many years, is that if you have a joint distribution that factorizes according to the structure, the macro structure I gave you before, then you have some conditional independencies. So for instance, in this case, you've got that x2 is independent of x4 given x1. You've got that x4 is independent of x1 and x2. So whenever you have a causal model, you have automatically, in a way, for free, some conditional independencies implied. This has nothing to do with causality at this stage. It's purely statistical, but it has profound implications. And you see why. But what makes a DAG really causal? That's the issue. So we all know that. We all know the joint distribution. That has been around for many years. But what makes it causal? And here is the point. If you externally force a variable to take a particular value, that's what we call intervention. So think about the gene expression. You force one gene to become silent, then that makes the variable independent of its causes. That makes sense. You force something, and so the original causes disappear. Now, this is associated with two operations on a graph, the do operator and the graph surgery. They are basically the two sides of the same coin. Here it is. Suppose you start with 3 variables and you have a graph connecting them. And now, suppose I intervene on x2. So I force x2 to take on a particular value. I do x2 equal x2. Then that's the answer. One of the variables becomes a diamond. It's no longer a circle, but that's simply because it has been forced to take one value. But most importantly, the connection between x2 and x1 disappears. Yeah. Okay, so the original cause has gone away. And this is what we call graph surgery, because it's like cutting one of the parts of the graph. Here is another example. You intervene on x3, and that's the graph surgery taking place. You remove the connection between x1, x2, and x3. Now, intervention and conditioning are different. That's important. For us being brought up dealing with probability ideas, we know very well the importance of conditioning, of conditional probabilities, conditional distributions. But intervention is not conditioning. So conditioning is passive, while intervention is active. Think in this way. Passive in the sense that it's not you acting upon the system, it's the nature that works for you and produces whatever it produces, and you observe. Now, the fact that conditioning is fundamentally different from intervention is because when you look at conditioning, you actually observe the activity, say, of the gene, but that provides information also about the driving factors. And that's why the two things are not the same. Let me give you, again, a toy example to show this. So you have the 3-variable case, you intervene on x2, that's the graph surgery taking place, and suppose you want to compute the interventional distribution. What the distribution of x3, thinks of x3 as, say, the outcome, given the intervention, I would say. So do x2 equal x2. Well, that's what you get, because by looking at the new factorization of the graph, you've got p of x3 given x1, x2, that's fine. But you no longer have p of x1 depending on the variable x2. That's link has been removed, and so you marginalize with respect to the marginal of x1, p of x1. Conversely, if you have the full graph, because it's an observational setting, you're not intervening here, you just observe, and you want the conditional distribution of x3 given x2, not do x2, but given x2 in the ordinary way, what happens is that now you have to marginalize with respect to the conditional distribution of x1 given x2. And that explains why do and conditioning are not the same. That's a crucial distinction. So as Per says, if you want to do causal inference, you have to go beyond statistics. I know it's hard for us because it's like being well considered not so smart, but of course the idea is that there are two different aspects, and so we have to take that into account. So this is another example which is perhaps a bit more concrete. Suppose you want to investigate the effect of enforcing a gender-blind hiring policy. So you want to tell your recruiting team not to look at the gender of the applicant when deciding upon whether to hire it or not. Well, in a very simplified setting, so assuming that other factors that of course influence hiring have been controlled, you've got 3 variables here. The team culture, say progressive and traditional team members. You've got the policy, gender blind or not gender blind, and then you've got the hiring, say of female. Well, that describes the situation. Now, the problem here is that there is confounding given by the team culture. The team culture is influencing both the policy and presumably also the hiring. So if you look at it from the observational perspectives, you want to compute what's the probability of H equal 1, say, hiring a female, given that the effect is on, and that's what you would write from a probabilistic perspective. You marginalize with respect to the conditional distribution of C given P. But that's not what you want. You want to see the causal effect of enforcing on everybody the policy of gender blind, and then because of the graph surgery, you would have to average with respect to the marginal distribution of C. All right, so the interpretation is that in observing P on answers the question who chose the policy. So what is doing the policy for people who chose it? Whereas intervening do P equal on answers what if everyone were forced to use it? So it's a different thing. Causal graphical models are great. Just drink a bit. But they must be supplemented with other tools for doing other type of jobs, as I will explain, and in particular, structural causal model, SCM, are instrumental in this. So what is a structural causal model? A structural causal model is a pair made up of a set F of assignments. Think of the assignments as a deterministic mechanism that tells you how Xi is generated. So there is a function Fi, which depends, again, on the causal parents, and you can call it a noise variable, or you can call it a background variable, UI. And then there is a joint distribution for these UIs. So that's a structural causal model. So, for instance, before doing that, how do we link the structural causal model to the causal graphical model? Very simple. The causal graphical model induced by an SGM is the directed graph with vertex set, the variables, and directed edges from each vertex to the from the parents to the variable. So for instance, here you have it. If x1 is just a function of the noise, x2 is a function of x1 and the noise, and x3 is a function of both variables and the noise, this is what you get. Very natural. I mean, there is a perfect duality between these two methods. But then why do we use structural causal model? And we just don't stick to causal graphical model. Well, the reason is that structural causal model actually are richer. And in particular, they might consider models that have got cyclic causal relations. That's going to be, you know, like a headache. You know, a cyclic causal model is complicated. But there are situations in which this might occur. But in that case, quite a lot of things break down, and you don't have the equality between the two. But usually we enforce acyclicity, so that's the induced graph is actually dark, and we enforce something stronger, which is called causal sufficiency or no hidden confounders. That means that you can take the joint distribution of the UIs to be independent. But that's not the only reason why structural causal models are in a way better than causal graphical model. I'll tell you in a minute. How do you modify your structural causal model if you make an intervention? So we know what to do with causal graphic. We know what to do with the graphs. What do we do here? We do exactly the same thing. We're just, you know, we apply to this situation. You replace, if you intervene on Xi, the ith structural equation by just writing Xi equal to Xi. So you don't have the function anymore. It's just a fixed value that you impose. And the remaining Fj's remain unchanged. That's crucial. I mean, if you're talking from a mathematical perspective, you just say, all right, okay. But from a practical point of view, saying that intervention on Xi is going to leave the rest unchanged is a major assumption. It means that there is a sort of stability of the system to external interventions. And this is one of the current problems in machine learning, actually. How do things change when I change environment? Again, something will be done. Now, you then have what I wrote as a M super do Xi equal Xi. That's a new structural equation model. You see, you've got your F prime. And the difference is that now everything is the same except for the function related the Xi to the parents. And similarly, you have the interventional graph, which is exactly what we know already. So this is the situation. Suppose you fix x2. What changes is that now x2 is fixed, and that's, of course, the corresponding graphical model from the causal perspective. The two things are working parallel, so it's something we have already seen. One of the major contributions of Judea Pearl, in my opinion, was to classify clearly 3 tasks that scientists have to face when they deal with data. And he invented this concept of the ladder of causality. Everybody knows what's the ladder? Ladder is scala in Italian, right? So it's nothing new. And then there are the rungs, the level of pioni, okay, of the ladder. So here's the idea. You have a level 1 association. You see things. That's the most simple thing. That's probably what we've been doing many years ago, looking at things and trying to describe the association. The second level is intervention, is doing something, is intervention of something. But there is a third level, which I haven't discussed yet, and it's the counterfactuals. Now, counterfactuals is imagining. Now, in my opinion, what characterizes us as human beings? I believe imagination. So it's a truly human thing. And we want to see how we can formalize it from a mathematical and probabilistic perspective. Here's the ladder. And remember, observation is passively seen or measured. Intervention is external manipulation or experimentation. And counterfactual, here is the issue. What would have been given when something else was in fact observed? So you observe somebody who got a disease and got a treatment, and you ask the question, what would have occurred if I had changed the treatment? That's a tricky question, because now you've given the treatment, and the person has developed some characteristics. How can you do that? Well, you will see that the causal graphical model is not strong enough, but the structural causal model is good enough for that. So counterfactuals are actually to be dealt with through a structural causal model. There are issues with counterfactuals. They cannot be observed empirically. You cannot see simultaneously a person having treatment A or B. And so some people call it unscientific, some people call it problematic, but there are actually psychological investigations that show that we as human beings start thinking counterfactually from a very young age. If you take a kid, a very small kid, he or she is already thinking counterfactually. And you can see from the question he or she asks. So we have to deal with that. Given that patient X received treatment A and their health got worse, what would have happened if they had been given treatment B instead of else? Instead, all else being equal. All else being equal is in italic because it's important. I don't want to change the reference situation. I would like to imagine like a new world, a counterfactual world, in which I apply a new treatment, but I want to preserve the characteristics of the system, of the patient. And structural causal model provides a suitable framework for this. So here's the idea. Observing what actually happened, remember, you see that the patient got the disease, provides information about the background state of the system, which we also call the noise term. That's the crucial link. So how do we incorporate the evidence that we collected? We change the structural causal model. And we change it by modifying the joint distribution of the background variables. And you will see at the very end of my lecture, if I get to that, I hope so, that this is one of the major obstacles now in machine learning. The calculation of this incorporation of the evidence can be massive in terms of computation. But there are ways to do that. So this differs from an intervention where such background information is not available. So counterfactual is not intervention. Intervention is doing, counterfactual is imagining a new world. So here is the idea of the counterfactual in structural causal model. Given evidence X, you observe a structural causal model, observe from a structural causal model, the new counterfactual structural causal model M super X equal X is obtained by updating PU to the PU given X. So you update the distribution of the background variables. And then counterfactuals are then computed by performing interventions in the counterfactual structural causal. Yes?
This is the neutral condition in this.
Yeah, this is a conditional distribution. Yeah, it's this is our, yeah, this is the probabilistic. Yeah, it's not a do thing here because this is what you observe. Yeah. How you compute is another matter. In fact, that's something, you know, maybe Bayesians can contribute a bit on. Yeah, absolutely. Toy example. You just have two variables, x equals the noise, y equals 3x plus uy. And ux and uy are IID, say, normal 0, 1. Now, you observe x equal 2 and y equals 6.5, say. And want to answer the counterfactual question, what would y have been had x been equal to 1? Well, here things are so straightforward where we do it clearly, but, you know, think of a system that has got hundreds of thousands of variables, for instance. So we are thus interested in this new thing, the probability relative to a structural causal model in which we have incorporated evidence, that's the x equal 2 and y equals 6, and moreover, we do an intervention. How can we do that? Well, easy here. X is the noise and y is 3x plus the noise. Now you update the noise distribution. How? Well, ux with probability 1 must have a distribution that is a mass at 2 because you observe 2. And uy must be 0.5 because 3 times 2 is 6 plus the noise, but you observe in that case 6.5. Either way, this is very crude because it's like not taking measurement error into consideration. And that's the snag. I agree with that. But that's what typically people do it. Okay? And you obtain the updated structural causal model and then perform the intervention. And what you get is that in this case is a point mass again of 3.5. So having incorporated the information is like having incorporated information on the background noises, and that gives you that the result of y would have been 3.5. Now, is this different from the standard, well, standard in quote, intervention? Yes, it is. If you just do the standard intervention, it's not conditioning, remember, it's the second level, well, you get a fully stochastic distribution for y, because in this case, it's very simple. It turns out that it's a normal with expectation 3 and the variance is 1. Because you condition on the fact that x is equal to, you don't take into consideration the structural causal model, you just do y to x equal 1. So there is a difference between the two. So I'm getting towards a risky area. Yes, yeah, you're right, I'm afraid. Okay, so I will jump some. Don't worry, I skipped something, so it's not a problem. I want to go back to the issue of factorizations, because it's something that, yeah, exactly. I think it's, we agreed on 45 minutes. I want to go back to factorizations. And I don't want to look at it from the mathematical perspective. I want to look for a more concrete perspective, especially for a machine learning perspective. I'll try to make this clear. We all know that there is a relationship between altitude and temperature. The higher you go up, the lower the temperature in general. Okay, we can jointly discuss the distribution of the altitude and temperature by writing PA, margin of A, times P of T given A. But of course, I could write it also the other way around. Probabilistically, the two things are absolutely equivalent. I want to convince you that this is not the case if you want to set up a causal model. Why is that? Well, from the very word that have been used, disentangled versus entangled, you can get the feeling. Entangle is messy, and disentangle is clean. And we like clean things. But why so? here is the catch. In the disentangled factorization, some components, think of the two conditionals, one is the marginal, but the two general conditional distributions, as components of your system. Well, in the disentangled factorization, they generalize across domains. Here is the idea. Consider two countries, Austria and Switzerland. Well, they're two sort of similar, but not quite the same, of course. There are mountains in both, actually. I believe Switzerland, no, sorry, Austria has got higher mountains. Samuel Powell, do you confirm? I think Austria has got higher mountains on average than Switzerland. Now, this is the disentangled factorization for Austria and Switzerland. And what you see is an interesting thing. One of the conditionals does not depend on the country because there is a physics law behind it that tells you how temperature evolves with altitude. And so presumably, I mean, unless you change, you go to Mars, something else might occur. I don't know the physics of Mars, but the physics on Earth, especially in our part of the world, work clearly. We know what it is. And so P of t given A generalizes across domains. What might change is the marginal distribution of the altitude across the two countries. That's fine. On the other hand, if you go to the entangled factorization, everything becomes messy. Both change because you lose the fact that one is stable and this is going to have consequences on the fact that you have to change both. Why is that important? Well, it's very important because if you try to set up a system that is robust to intervention, think of this like an intervention or distributional changes due to the domains. Well, you want to have a system that is robust against changes. So the joint distribution should be disentangled as much as possible. And this is the principle of independent causal mechanism. The causal generative process, think of the structural causal model as a causal generative process, is composed of autonomous modules that do not inform or influence each other. And that's why we could think of graft surgery. So intervention just locally acts. It doesn't change the system, it just acts locally. And this principle of sparse mechanism shifts. Small distribution changes manifest in a sparse or local way in the causal disentangled factorization. They should not affect usually all the factors simultaneously. This is important because think of autonomous driving that we all speak about nowadays. Now, what's the problem? That you train your model on specific set of roads. But of course, the model is trained on, say, Los Angeles, and you bring it down to Padova. Well, you change the environment, inevitably. And then things can become really crazy. Why? Because the system is maybe not sufficiently robust. So it's a crucial idea for people developing autonomous driving systems to have situations in which you can sort of model a causal mechanism that does not change the interventions. Causal discovery, I think I will skip this, although it's crucial, of course, but so far we have assumed a given causal graph, DAG, possibly based on domain knowledge, but we typically don't know. Can we do something about it? Well, the answer is yes, but I will. One of the problems in finding the true causal graph is Markov equivalence, the fact that by just looking at observations, you actually see not the causal graph. Okay, so let me just give this picture. Suppose you got these three variables, and these are three ways in which they can be related. They are different, of course, causally different. And then there is this part here. Now, the fact is that from an observational viewpoint, you cannot distinguish between A and B. You can distinguish between A and C or B and C, but you cannot distinguish between A and B. And that's a problem, because if you just have observational data, not interventional data, you are in a mess, because A and B are equivalent. In particular, they imply the same conditional independence. X independent of Z given Y, and no other independencies. Whereas on the other hand, on C, you've got X independent of Z, but not X independent of Z given Y. And so this is going to be a problem, but there are ways to characterize the Markov equivalence and solve the problem. Let me skip this. Let me go to causal reasoning and then jump to the conclusions. So causal reasoning starts from a known or postulated causal graph and answers causal queries of interest. And there are two steps in this causal reasoning framework. One is to identify the query, i.e. derive an estimate. What is an estimate? Is a well-defined expression in terms of observable quantities. That's crucial. We ask a causal question, but we want to give an answer that we are able to eventually estimate. That's why it's called an estimate, using data, observational data, and make inference on the estimate using data. Of course, you can use interventional data if you have them, but that's typically not the case. I mean, randomized controlled trials are still great if you can do them. I can skip this, but this will be the crucial step. When you have a causal graphical model, no hidden confounders, or a structural causal model, the starting point is this. You intervene exogenously on a variable xi, so you do xi equal xi, and that's the structure of the joint interventional distributions. You see what it is? It's exactly as in the Markov structure. You've got the product of the conditionals given the parents. The only difference is that xi is now being forced externally, so there is a mass at xi. This is the stability principle, the principle of sparse mechanism I was discussing earlier. That's the starting point. If this fails, then your model is not going to be robust. And then, whatever you're interested in the effect on, say, a variable xh, then you marginalize what is in G. G has been called the G formula by Robbins, or is truncated factorization by Pearl. And it relies on the independence of the causal mechanism. And I had this toy example, but I can skip on this. This is the adjustment sets. It's interesting. Back to counterfactual inference. You can think of the steps leading to counterfactual as 3 steps. One is called the abduction. Update beliefs about background variables. We've seen that is the distribution of the U given the evidence. Then the action, you modify the model by applying an intervention. That's your counterfactual value. And then your prediction, you want to propagate this modified model forward using the updated distribution. Now, what's the problem? The one I was mentioning a few minutes ago. Abduction requires large computational resources. And so even if you start with independent noises, as soon as you condition on the evidence, this destroys the independence. So it's necessary to carry over a full description of the joint distribution. This can be massively time-consuming and expensive. And so it is a brilliant idea that was developed a few years ago, is to represent the problem as a twin network. What is a twin network? It consists of 2 interlinked networks, one representing the real world and the other the counterfactual world. So here's a sort of toy picture of this. On the left, you've got the factual world, and you carry it over, that's the dash arrows, to the new counterfactual world. The idea is that you preserve the structure of the background variables that you learn in the factual world. And here is a recent paper that appeared in Nature Machine Intelligence, in which they did implement this strategy of twin networks. But the good news here is that they tried to solve the massive computational problem of abduction by using a neural network. And here is what I was trying to say at the beginning of my lecture, namely the interplay between statistics and machine learning. Here we have methods that use neural networks that do take into consideration the structure of the causal model you started with. So it's really a synergy taking place. And this is an application that is nice just to see that what I showed is not just pictures. There are real problems behind it. And this is a nice example. It's in a paper in journal Series A, and then it's also in this Nature Intelligence Machine paper, in which the problem was this. Children were exposed to high bacterial concentration in their drinking water, developed diarrhea. What's the probability that it was the bacterial exposure, not something else, that caused the disease? This is also called sometimes the probability of causation. It's really important for policy, because what was the policy implemented here? You can see in the top picture. It was to create some concrete structures to have the water not contaminated with the field, the terrain, and then to have installed pipes so that the water is actually flowing into clean pipes. Well, to cut a long story short, it was found that in this case, the probability of causation was rather small. Despite a randomized controlled trials showing that, it is good to create concrete and good pipelines, but for this particular community of people, the probability that an intervention would have, on these particular people, would have eliminated diarrhea was about 0.12. So that's something that has got some policy implications. Conclusions. We have seen, remarkable achievements by machine learning and AI for predictions. Fantastic results. Think of image recognition. But this system become increasingly integrated into new applications, medical, autonomous driving, I mentioned already. And they face severe limitation because you change the environment and basically you want to have external intervention taking place and you want to be facing these issues. And causal models are, in my opinion, in the opinion of some smarter people than me, the way to go. In particular, causal graphical models promise to be especially suitable when applied to AI systems. Robustness can be enabled. Interpretability becomes more transparent because you look at graphs representing the causal structure behind it and explainability. And let me conclude by just giving you 3 references. One is the book by Julia Pearl and the journalist, scientific journalist Dana McKenzie, The Book of Why. It's a great book. So you should all read it. It came out a few years ago. It's written in a very entertaining style because there is also a scientific journalist behind it, but it's full of good concepts. And it ranked very high in the New York Times best books of a few years ago. So something I can really recommend. On the right-hand side, you have a more, serious, solid book on the elements of causal inference from the graphical models perspective. But remember that there is a whole session at SISBayes 2025 devoted to Bayesian causal inference. So when you go to that, you see a more balanced picture. You will not see graphical models, but also something else. And finally, this nice conference proceeding paper that I relied a lot to write these slides by Bernard Scholkoff, in which the basic ideas were presented. Thanks very much.
Thank you very much, Guido. We have time for a few quick questions, if any, from the audience.
Thank you. Just a minor question, or maybe not so minor. What was a probable cause in the Kenyan example? Because you told us that that one wasn't a probable cause, and I guess you need another one to make a convincing case for not doing that.
I'm not sure they actually managed that, but it's probably the fact related to what they were eating. It's not just what they were drinking, but also the living conditions of what they were eating besides the water that created the bacteria, proliferation and leading to diarrhea.
Thank you very much for the nice talk. You had one part that you had to skip a bit for time reasons about learning the graph. So I was wondering, are the methods that are used to learn the graph structure that are currently used, mainly Bayesian or not, and which kinds of methods are,
Yeah.
let's say, the most popular now?
Okay, so of course, we statisticians are well equipped to learn.
Guido, just because I want to repeat the question because it was not hearable. The question is about which technique are used to learn the graph in this setting, Bayesian, not Bayesian, and the differences.
Yeah, so statistics is an area where, model choice has been a hot topic for many years. It's still a hot topic, in my opinion, still a great topic. So we can contribute a lot. And indeed, these contributions have been used. So one is the so-called constraint-based methods. And so the structure of the graph can be learned using observational data by just looking at various conditional independencies. There is the celebrated PC algorithm that does a nice job. What's the problem? You don't learn the causal structure exactly, you learn the Markov equivalence class, okay? And then you have to rely on extra heuristics to get to the DAG, or you can rely on extra interventional distribution. So you have your observational distribution, you get to the Markov equivalence class, you supplement that with interventional distribution. So I can speak about my own work now. So I did a work with actually Federico, I think is around here. Oh, that's it. And so where we try to blend observational and interventional distribution, and actually you can get to the causal Markov structure in that way. Now this can be Bayesian or not, and if you use the Bayesian approach, typically what's done at the moment is well, it's something that is Bayesian only in name, is big, which is not really Bayesian, as we know, because you have to. It's quicker. So something can be done to make things more nuanced.